worth a tenth of the total grade, 10%. So you're definitely going to want to do it, unless you feel like blowing off a letter grade. That's probably not the case. So if we go to contents, and I'll post a folder with a link to it as well. There's a document called Project Ideas. And those of y'all who have taken my classes in the past, be it in this language or other ones, may recognize some of them. Just don't do the same one that you've done in the past, right? If you did the fighter simulator, then don't do this fighter simulator again. And if you don't like any of them, then you could come up with your own idea. You just have to run it by me and also make sure that it's not too difficult for you to accomplish in like the next 3-4 weeks. So the calculator project is kind of weird. I'm almost thinking about getting rid of it. But the idea is, it shows this great big thing here, and so people think that they're going to write a graphical user interface that uses the keypad. But actually, what it is if you use this keypad, the way that it was set up, it would generate numbers. And then the point of the project is to decrypt those numbers. Not really decrypt, it's just simple numbers. There's each keypad, keystroke sets a binary value. And then so you would be given a series of values that represent the binary values that were typed in. And so, for example, let's see if we can find a good example. If they type a 7, that lights the 1 light. I know you can't zoom in there and see, but it's got 1, 2, 3, 4, 5, 6, 7, 8. 7 goes down like that, and 7 also goes down like that. And so it lights up that bit and that bit, which adds up to 136. And then they want the plus button, which lights up that bit and that bit, which gives us a different number, an 18, and so on. And so your program will just need to accept these numbers, like 136, turn it into a 7, because that's what it really is, and an 18, and turn that into a plus sign, because that's what it really is, and then do the series of math. So if 136 is a 7, and 18 is a plus, and a 132, if we checked up here, ought to be a 44, a 4, and then a 4, and then they hit the enter button, which is this. I don't see the enter button. The equal button, which lights up those. And then it would print out, these are the values you would get. And so you'd have to do this calculation, because that's a 7, and that's a plus, and that's a 44, a 4, and a 4, and that's the equal sign. And so you'd add that up and get 81 out of it. So it's kind of a neat one. It's probably the one I would do. Now, if somebody ever wanted to make something that generated that sequence of numbers based on a graphical user interface, that'd be pretty neat. All right, Caesar's modified cipher. Well, to know what we're talking about there, we need to know what a Caesar's cipher is. And there's a big explanation of what a Caesar's cipher is in there. A Caesar's cipher is just one where you translate. It's a substitution cipher. You probably have the idea of a substitution cipher where if you had these letters, A, B, C, D, and E, and you decided that you were going to replace all of these with a different letter, like what if you had J, K, L, M, and N. And so if you had the word bead, well, you just look it up. I'm going to write down a K, and an E is an N, and an A is a J, and a D is an M. And so that's my encrypted word. Enciphered is a better term. It's not really encryption, but it is enciphered. And then to translate it back, you do it the other way. Okay, a K is a B, an N is a E, and a J is an A. Okay, so how are these values calculated? Well, in the simplest form, Caesar's cipher, it's just the same alphabet shifted to the left or to the right. So you may say, I want to shift everything like this. And this will be W, X, Y, like that. And so if we go to write B, E, A, D, it'd be the same thing. That's a Z, that's a C, but you get the idea. I took the value of a B, and I added 2 to it. Looks like I subtracted 2 from it. Do that again. We have B, E, A, D. So a B, what's 2 more than a B? C, D. What's 2 more than an E? F, G. What's 2 more than an A? B, C. What's 2 more than a D? E, F. So now that is encrypted according to Caesar's cipher. Right? You write that message down, your runner delivers it to the generals, and hopefully they know the correct places to shift the letters back. Now, since we have ASCII characters and numbers and symbols like that, it's a little bit more complicated, but not much more. So there are a couple of projects here based on Caesar Cipher, just because that's a popular one for people to do. And one of them people did in the basic Java class. And so if you want to do another Caesar Cipher project, I needed to come up with something a little bit better. And so here's the more complicated version of it. Let's go down to the simple one. The simple Caesar Cipher, the program should let you type in a value. Ooh, wouldn't it be nice if it was formatted correctly? Ask for input. Please enter a sentence to encipher. And then it shifts it. Shifts it once. Well, if you don't shift it at all, you get the same input, right? You know, if an A becomes an A and a B becomes a B, and this is great. The people who are watching the video, you know, online aren't going to get to see what I wrote on the board. Okay. Anyways, there's adequate explanation of what a Caesar cipher is in these documents, and you can read up on them. All right, and so shifting it once, all A's become B's, all B's become C's, all C's become D's, and so on. And so you just write a program that would shift it with values all the way from 0 to 94. And if you shift everything 94, wrapping around at the edges, then you get your original string again. So then if you took a message that was generated by using the cipher, you plugged it in and did the same thing, then it would eventually give you the correct message, right? You know, so if I took this one and I used that one as my input, if I copied and pasted that my input and I ran it again, another shift version, eventually we'd get to see one that actually revealed our text. So I'm going to give you some text that I want you to decrypt based on writing Caesar cipher, shifting everything 1 all the way up to 94 times. Then you'll get to see the message. You'll know what it is. It's very obvious once you do it because it's written in English. So that's Caesar cipher. That's one of the versions of the projects based on Caesar cipher. Caesar's modified cipher. For the people who've already done Caesar cipher, then what I want you to do is also implement something called the modified cipher. And the idea behind the modified cipher is that instead of just shifting everything by 1 or 2 or 3, whatever your shift value is, that's what you use for the first character, but you increase that by 1 for the second character, and you increase it by 1 again for the third character, and so on. So an ordinary Caesar cipher looks like this, right? If we start off with an A and we want to shift everything by 10, well, an A's ASCII value is 65. We add 10 to it and we get 75, and the resulting ASCII character from that is a K. And a B is a 66, so we add 10 to it, we turn it back into a character, we get an L. A C is a 67, and we add 10 to it, and so on. And by the time you get down to these lowercase letters, they need to kind of wrap around to the beginning of the ASCII chart for reasons you can read about. And so when we take a Y, which is 121, it's going to go up to 131, but that's past the end of the ASCII chart, so we have to subtract a value. We get 37, and that's a percent. And then if you're going to decrypt it, it's just the same. We encrypted this string. We got that one. Now we're going to use that as our input, but we're going to say shift it by -10. All right. And we get our original answer. For the modified one, the first letter you shift by your value, but the second letter you shift by that value plus 1. The third letter you shift by another, you know. And so that makes it considerably more difficult. I mean, it'd still take the NSA like 0.0001 nanoseconds to crack it, right? But if you handed that to somebody and you said it was written in Caesar cipher, they would not be able to get an answer. If you took this string and fed it into that first program that I showed you, you wouldn't get any deciphered version that would make any sense whatsoever. And to make it even harder, you could specify by what values this increases each time, right? Maybe it doesn't just increase by 1 each time, maybe it increases by 2 each time or something like that. So it's just a more sophisticated version, one that's a little more difficult to crack. And again, there's a lot of explanation about how it works. I don't think I even give you an example output. I should go ahead and generate, you know, this is what I would like for it to look like. But what do? You ask for some input. You ask for the shift value. You know, the quick red fox is your input. 10 is your shift value. Whether you want to encipher or decipher, and the method to use. Method 1 is just a modern Caesar cipher, just like the other document. And method 2 is the modified one that's shown on the last page. That makes sense?
So we can do that if we did Caesar
Exactly,
cipher?
right. If you've already done a Caesar cipher in another class, you can go ahead and do this one as well because it's got extra stuff in it. Selection sort versus bubble sort. I think I've shown you all the selection sort. Have I not?
Yeah, I remember I said that.
Yeah. We watched that video, that awesome video. Okay, and then the bubble sort is just another kind of sort. And I give you some source code for implementing those, but they're in Python. You would have to change this into Java. Even if you don't read Python, you could change it to Java. And I give you hints about, the changes you'd have to make. But anyways, so I give you two functions, a bubble sort and a selection sort, written in Python. I want you to convert them to Java, and then I want you to make a very specific change, which is to find out how many swaps each one does and how many comparisons each one does so that you could compare their performance. Now really, under many circumstances, the performance is going to be about the same, but in certain circumstances, the performance would not be the same at all. So if you feel like doing a sorting project, one that you have already some kind of sample code in order to use the pseudocode, I don't want you to go and copy and paste I don't want you to copy and paste swap code from the internet, right? Instead, I want you to use these because I'll be able to tell, that it was written from Miner, or else you copied it. No, I don't want you to copy it, from the internet. The monster array. The idea behind the monster array is that we create an array. This ought to look familiar for those of y'all who've done the recent homework, right? We have a 2x2 array. Well, it's more than 2x2. It's 8x8 or something like that, filled with numbers. And what we're going to do is we're going to plop something down. We're going to say that a monster starts looking for the largest number. Starting from position 0, 0, he's supposed to make a beeline to the largest number. So here we go. That's our starting position. And there's the monster. Well, the 7's the highest one. So he's going to move there. He's going to move there. Now this is following a very simple algorithm to determine which way he's going to go to find the largest one. Eventually he goes and he claims it, right? Now there's no more 7's on here. That was the highest value. It finds the newest highest value and it starts looking for it. And then, it goes down to 6 and so on. And then finally, when all the numbers are gone, when there's nothing left but, zeros on your chart, zeros and negative ones, I think I said that would be the replacement value for that, then the monster's reached its target. Elaine might like that one. She's interested in 2D arrays. I'm kidding. You can do any of them that you want. Deciphering a substitution cipher. I've already talked about substitution ciphers. What I'm going to do is, if you want to do this one, I will give you some encrypted text. And it'll be different for each person. And I will give you something very important, which is the frequency list of the most commonly occurring letters that appeared in the original document. Because like if you're trying to crack a code, you can look up tables that show that E's appear more than R's in the English language, and S's appear more than T's and stuff like that. Well, according to the document that I encrypted, the original one, these are the most common letters in it. Spaces occur more than anything else, right? Because spaces break up the words. And then there are more E's than anything else. And then followed by A's and so on. So you have some encrypted text in a file. It's going to be a lot longer than that, right? But it doesn't really matter how long it is. And then I'm going to give you that. And what you are going to do is you're going to run through the encrypted text, finding which letter occurs the most often in it. But it's not going to match that, right? But instead, we would go all the way through this top encrypted text and find the one that occurred the most often, which is an exclamation mark. And then we'd find the one that occurred the second most often, which is the F, and the one that occurred the third most often, which is the B. And then you would translate that encrypted text by saying, okay, every exclamation point must have been a space, and every F must have been an E, and every B must have been an A. Now, if you look at it, you can tell it was a Caesar cipher just with a shift value of 1, right? A's became B's, S's became T's, and so on. Now, there's no guarantee that I'm going to give you something that was done with a Caesar cipher. It may be substituted based on a different value, but the way you would solve it is the same. You don't care how I encrypted it, how I enciphered it. You just need to build this list here. I give you this list, which will vary a little bit based on each document, and then you do a substitution. Well, the most common one was an exclamation mark, so I'm going to replace them all with spaces. And then E's were the second most common. I'm going to, F's were the second most common. I'm going to replace them with E's.
So we don't know how to work with files yet.
Right. We need to do a file program in order to do this. Fortunately, it's really easy. It's as easy as reading from keyboard input. So, that's a good one to go for if you feel like it. All right. Fighter, J-Fighter. Those of y'all who've had my class before have heard this explanation several times. I'm not going to go deeply into it because you can read the rules, but what it is you let the user enter a name, a health rating, an armor rating, and attack dice for 2 characters, like Dungeons & Dragons characters or video games characters or whatever. And then this just messes up all the spacing and stuff like that. I need to save it as a PDF because that looks pretty pitiful. And then what's going to happen is the game is going to sit there doing battle with the 2 based on the rules listed here. And the fact that the thing is 5-6 pages long doesn't mean that the rules are that complicated. They're pretty simple. It's just I explain it 3 ways. I explain the rules one way, I explain it another way, and then I show you actual output of the program. So we have Conan versus Trogdor. They have the same ratings or something like that. So we'll come down here and we'll see it. Conan has a health of 10, armor of 1, and rolls 5 dice. Trogdor has a health of 10, armor of 1, and rolls 5 dice. So Conan rolls 5 dice and gets a roll, including a health bonus, which is half your health. For that, he got a 22. Trogdor rolled his dice and got his bonus and added that to 25. So Conan was outmatched, right? Trogdor generated 25. Conan generated 22. The difference between those 2 values is 3. Apparently I need to update this because it says damage is 2. Yeah, 24, 25. Okay. I'll rerun the program, make sure these look right. Anyway, so the damage is the difference between those 2. Conan should have taken it. However, Conan has some armor, which absorbed one of those hits, so he only took, 2 hits. Looks like this would have been correct if that was a 3 rather than a 2. And so on. You just keep fighting until one of them reaches 0 health. And since you get a bonus for your health, and then the more that you lose, the faster that character starts,
So
the lower his rolls are. Yes, sir.
what do I do if I did that last time?
Well, I'd rather you pick another project, but if you think that you could... Which class did you do that in?
Java.
Right, I don't want you to do it again in Java 2. Right. Pick another one. Or come up with some other game system to emulate, not this one. Right, you can pick your own project. Just, I don't know how you would make it better than you did last time, because you did a good one. The only thing you need to worry about is that if their armor is too high, then neither one of them ever take damage and it'll go forever, and I want you to figure out a way of stopping that.
Oh man, I did that. I threw up so much data and armor on those characters and just watched it go forever.
Yeah. So there are ways of solving that, right? You could make it so that their armor degrades over time, or that if Conan's armor absorbed 2 points, but that would degrade the armor by 2 points and his armor is less. Something like that.
What I chose to do was that, regardless of how high the armor was, they'd always get hit by 1 inch. Because I play a game that always does that, where no matter how high the defense is, there's still a minimum amount of damage.
Right, if there's a minimum amount of damage, the game's not going to last forever, so that's a good way to do it. Yeah. Yeah. All right, so those are the project ideas. If you don't like any of them, come up with your own, but like I said, make sure it's not too difficult, but also not too simple, right? I can work with you if you need other ideas, or I'd like to hear from you about your ideas. Make sense, gang?
And Hangman has been banned.
I didn't put Hangman there. The problem with Hangman is that everybody takes Hangman off the internet, but y'all wouldn't do that.
Well, I thought that's why you removed it, because everyone cheated on it.
Yeah, it's been heavily cheated upon in the past, right?
Wait, so there was really a lot of people who copy and pasted Hangman
You'd be surprised.
Oh yeah, when I was at OU, our teacher was talking about how to program Hangman, and like she went on this whole thing about how to do it, and it's like, or you can just go on the internet and take it.
Yeah.
Oh,